Swayam Prabha. Digital India. Educated India.
So far, we have been looking at the motion of a single particle or a collection of particles, but only that of its CM, that is the center of mass. So, for example, if we have a collection of particles like this and I apply different forces on each particle, and suppose this happens to be its center of mass, what we have been looking at is how the center of mass moves. That is, the equation that we had been solving in the previous lectures was the total mass m r cm double dot, where double dot refers to the second derivative of the r vector, is equal to total force applied, where m is the sum of individual masses, that is the total mass. The vector RCM is defined as 1 over m summed over mi Ri, that is a vector for each individual particle, and F total is the net force being applied on the system totally. Now, I want to look at individual particles, how its motion takes place. I want to go beyond the center of mass motion. So, for example, suppose I have these particles connected by a spring. For simplicity, I will just take 3 of them and I apply different forces on each particle. Let me name this particle 1, particle 2, particle 3. Let force on particle 1 be F1, let force on particle 2 be F2, and let the force on particle 3 be F3. As we apply these forces, in the next instant I could have a different situation in which the particles could be, maybe the spring has stretched. This, let us say, is a rod which is cannot change, and maybe this spring has stretched. Further, it could have changed its orientation, that is, if this is particle 1, 2 and 3, other situation I could have is maybe particle 1 is here, particle 3 is here, and this is particle 2. In other words, under the influence of these forces F1, F2 and F3, the body could deform, that is, the distance between the particles could change and it could change its orientation. Nonetheless, the center of mass still moves according to what the net force is, that is, the center of mass would still follow this equation. But in addition to that, the translation of center of mass, like a heavy point particle, under the net force, total force F total, there could be other things, and that is what I said, maybe the deformation, maybe a change in orientation. So, these are beyond the translation motion of center of mass, and this is what we are going to focus on. To start with, let us again separate the deformation motion and the change in orientation motion. So, I am going to make an assumption and this assumption defines what are known as rigid bodies the assumption is that given a system of particles, when I move them, so let me again number them 1, 2, 3, 4, 5. When I apply different forces on each of the particles, the distance between two particles remains unchanged. These distances remain fixed. Similarly, distance between this and this, distance between this and this particle, and so on. In other words, in the previous example where I took one rod, one particle here, and there was a spring here, I replaced this spring by rods that cannot change their length. So the distance between two particles would remain unchanged. You can feel right away when I apply a force, it is not going to deform. The only thing this body can do is change its orientation. So for example, 1, 2 and 3 could go to a different shape like this, different orientation like this, and this is known as a rigid body. In a rigid body, the distance between any two particles of its body remains fixed, and the only possible motion then is translation of center of mass plus a change in orientation. This is how we simplify the problem. The deformation part we can add later. For example, deformation leads to say wave motion or plastic phenomena or extension and shortening of say spring under a force. We are leaving that right now. Right now we are going to assume that the body is rigid. Take as an example again a body consisting of two masses which are attached to a rod of fixed length L. So I would call it a rigid rod, and this is a rigid body. Now if I apply a force here and a force here, let's call it F1, let's call it F2, what will happen is F1 and F2 have a net force. Let's say this is F1, this is F2, so this is a net force. So center of mass of this body would move in this direction. It would have moved. So center of mass would move, but the body could itself change orientation. It could be in this orientation. In general, I would require three variables to describe translation of the CM and three more variables to describe the change in a rigid body's orientation. You can think of these three variables to describe the change in a rigid body's orientation as three angles from three axes. So in general, what we learn is need 6 variables to describe the general motion of a rigid body. You may ask, why 6 only? In a rigid body there could be 10 particles, 15 particles, 10 raised to 23 particles. Why only 6? That comes because there is a big constraint we are working with. The constraint is no matter how many particles, the distance between two particles will always remain fixed, and that constraint reduces the number of variables that I need to describe the motion of a rigid body to 6. 3 of these are for translation, and 3 for rotation. What will happen if I take a rigid body? Now I can make it a general rigid body like this. All the distances are fixed between these points, and fix one point of this body. Suppose I pin it here, then it cannot translate anymore, and therefore I would need only 3 variables for describing its rotation. So I hope by now I have given you a feeling of what a rigid body is and how many degrees of freedom does it have when it moves. It has 6 degrees of freedom. On the other hand, if I fix one point, then it has only 3 degrees of freedom, and that is the change in that angles required to describe the change in its orientation. So that is the rigid body, and in next few lectures we are going to make this approximation that the bodies we are considering are rigid bodies and describe their dynamics. We start with simple problem of rotation about one axis, then we let the axis also move, and in third case we also let the axis change its orientation. So these are slowly we are going to build up these problems, but we are not going to consider the deformations. In that sense, all the body motion that we are considering are rigid body motions.